Today we're going to spend a bit of time looking at construction. Now, construction is an ancient part of mathematics, and it relies upon you using a straight edge. So you can use a ruler, but you're not really supposed to use the measurements on the ruler. You use a straight edge and a pair of compasses. Those are the only two tools that you're really allowed to use if you're doing this really properly. We're going to look at a few of the most basic types of construction today. We'll start with how you construct an equilateral triangle. You draw a straight line of some random length, and then you pull your compasses in and you put the point of the compass on one end of the line and the point of the pencil on the other end of the line. You get that as precise as you can. So point to pencil is the same distance as the length of the line. Now, to produce an equilateral triangle, all we have to do is draw a decent sized arc from that end and then again from this end. Now, the neat thing about the first arc is that all the points on that arc are equidistant from here. And if I draw another arc, then all of these points on the second arc will be equidistant from the right-hand side of my original line. And therefore it follows that this point here is special. It achieves two things at the same time. Not only is it the same distance from the left-hand end of the line as it is from the right-hand end, but also, because it's on the second arc, it also achieves the same distance in both of these directions. And so this must, by logic, this must be an equilateral triangle. Now, we're not allowed to use a protractor, but we can pull one in just to check that our result is correct at the end. We're not using it to answer the question, just to check our final answer. If I've done this properly, then this will be at 60 degrees. There you go. So that's how you can construct an equilateral triangle. Now, moving on to slightly more complicated things. Before we can consider other types of construction, you need to understand how a rhombus works, the properties of the rhombus. And there are three properties in particular that we need to think about today. In no particular order, if you draw in the diagonals of a rhombus, then they always, every time, they always cross at right angles. That's one of the properties of a rhombus. The diagonals cross at right angles. The second property is that the two diagonals bisect each other. So this length is exactly equal to this length here. It's also true for the other diagonal, but that's not so important for what we're wanting to achieve today. The last property I want us to think about today is that this diagonal here bisects this angle. It chops that angle exactly in half. And so we have three properties here. We could label these perhaps as A and B, and as C and D. And this diagram will be helpful to us as we progress through the next few examples. So first of all, we're going to look at how to construct what is called a perpendicular bisector. Now, let's understand what that actually means. We're going to start with a random line, and we are going to construct another line which does two things. It cuts this line exactly in half, so probably somewhere about here, but it also does so at right angles, such that the new line is perpendicular to the original line. Now it's helpful at this point just to consider the rhombus and how this relates to what we're trying to do. If this is A and this is B, then we could label this in the same way. And what we're trying to do is we're trying to find this diagonal, because after all, this diagonal crosses at right angles, that's the perpendicular idea, and it bisects this line. So if this is AB, then this AB, perhaps we can produce a rhombus sitting in here such that we get this diagonal as our final answer. Now, if you look at this, we're going to be starting at A and at B, and we need equal lengths in each of these directions. And that is best achieved by using a pair of compasses. So let's do that just now. Let's put the point of the compass on A as perfectly as we can. And let's start to try to find the top of the rhombus and the bottom of the rhombus. Now you're best to set this distance to about 2/3 or 3/4 of the length of AB. We're going to want to draw an arc up here and another arc here. Those arcs will not meet if we use a really tight circle, a really tight arc. But we don't want the arcs dropping off the page either. We don't want to make them too big. So about 2/3 or 3/4 of the length of AB is appropriate. So what I can do, I can draw in these arcs here. If I now repeat that procedure, compass point on B as perfectly as I can, that's pretty good. And then we're interested in where these arcs intersect the first arcs. So what we have now is we have the outline of a rhombus just here. We know that these four distances are all equal because we used the compasses, and we never changed the distance between point and pencil as we moved from one arc to the next. It was always kept the same. So these lengths are unquestionably equal to each other. That gives us a rhombus. That guarantees that this property will exist. This diagonal will bisect AB at right angles. And so if I now draw this in, then I have my answer. This is the perpendicular bisector of AB. There we go. I could bring the protractor in just to check that it is in fact 90 degrees. It's always a good idea to check your answers if you can. There we go. And if I wanted to, I could bring a ruler in and just make sure that those two distances are equal as well. That is the perpendicular bisector.